Hello everyone, this is the fourth lecture of third week. We were looking at optimization algorithms. We started with a very general framework of optimization algorithms, where you start with an initial point, choose a descent direction and the step size, and update the point based on the direction and the step size. You keep doing this iteratively until a stopping condition is met, right. So, for the previous two lectures, we learnt different kinds of algorithms for computing the step size, right. So, those are called line search algorithms. So, we learnt about exact line search algorithm and backtracking line search algorithm, right. So, yeah, what you see is the last screen of backtracking line search algorithm. So, I would like to add a little more to exact line search algorithm before going to the next topic. So, recall that in exact line search algorithm, so given xk and dk, we define h of alpha equals f of xk plus alpha dk, right, and we find that value of alpha for which h of alpha is minimized, right. So, one important question that we can ask is, for which kind of functions can we actually use exact line search algorithm, okay. So, we saw examples where we can use line search algorithms, right. So, for instance, if f is a function from R2 to R and f of x1 x2 is x1 squared plus x2 squared, right. So, we saw that using exact line search algorithm was fine. So, yeah. So, this exact algorithm can be used, But if we had a function of this sort, for example, then we saw that exact line search algorithm cannot be used because of intractability issues, right, analytical intractability issues. So, yeah, let us try to ask the question of when we can actually use exact line search algorithm and when we cannot, okay. So, there is one class of functions where we can use exact line search algorithms without any issues. What is that kind of a function? It is actually the quadratic functions, okay. So, here you are actually seeing an example x1 squared plus x2 squared, right. So, any function of this form, even when the domain of f is Rn, okay, you can actually use exact line search algorithm. So, the general form of a quadratic function when the domain is of dimension n is given by this form, half x transpose hx plus b transpose x plus c, okay. So, since we are actually trying to minimize f, you can see that the Hessian of f is actually h, right. So, h actually needs to be a positive definite matrix, okay. So, because in that case a unique minimizer exists, okay, and yeah, the values of b and c can be anything. B can be any n dimensional vector and c can be any scalar, okay. So, you can see that this is a quadratic function, right. So, for any quadratic function where h is positive definite, okay, you can actually use exact line search and there will be no issues. Okay. So, this is actually a quadratic function, yeah, this is a quadratic function, and yeah, exact line search algorithm can be used. So, yeah, instead of writing the full form as exact line search algorithm, I am just indicating as exact in the quotations. Okay, I suppose you understand that. All right. So, I am saying it can be used, you can ask how or what is the proof, right. So, I will derive the value, the precise value of alpha for any function of this form. Okay. So, I will do that right away. So, let us say f of x is half x transpose h x plus b transpose x plus c, okay, and we are given x k and d k. The question is, can we actually find alpha, right. So, let us check. So, now given x k and d k, we have h of alpha equals, let us substitute the values, half into x k plus alpha d k transpose h x k plus alpha d k plus b transpose x k plus alpha d k plus c, right. So, this is h of alpha. So, let us expand this. So, we have half into, so this is, so we will have 4 terms. So, we have 2 terms here and 2 terms here. So, on multiplying we will have 4 terms, it is x k transpose h x k plus, so you have alpha d k transpose h x k, and here you will have x k h alpha d k transpose. So, I mean both are the same. So, you will have 2 alpha d k transpose h x k, okay. So, the other one will be x k transpose h d k, but I mean since it is a scalar, the transpose of a matrix is the same value. So, that is why I have written 2 alpha d k transpose h x k, and then you have alpha squared d k transpose h d k. Okay. So, I have expanded half x k plus alpha d k transpose h x k plus alpha d k. Now, we will write down this term plus b transpose x k plus alpha b transpose d k plus c, right. Okay. So, now I will collect some of the terms, half x k transpose h x k, that is the first term, and plus b transpose x k, which is here, and plus c. So, you can see that this is actually f of x k, right. Whatever I have written down now is f of x k, we will use that, and then we will write down the others, which is the other terms. Okay. So, half into 2 is 1. So, it is alpha d k transpose h x k plus alpha squared by 2 d k transpose h d k, and yeah, alpha b transpose d k plus c. Okay. So, here again I will I mean rearrange this. Okay, c is done, sorry. So, yeah, so we have this term is over, 2 alpha into half into d k transpose h x k is over. Now, we have yeah, so alpha b transpose d k. So, I will write it this way, b transpose d k, and so yeah, we have alpha squared by 2 d k transpose h d k. Okay. So, you can see that the first term is f of x, that is very clear. Okay. Now, let us all f of x k. the first 3 terms. Okay. So, now let us actually find what is del f of x. Okay. So, you can so note that f of x k is half x transpose h x, sorry, x k transpose h x k plus b transpose x k plus c, and del f of x k is h x k plus b. Okay. H x k is a vector, H is an n cross n matrix, x k is an n cross 1 vector. So, it is n cross 1, this is also n cross 1. So, you get the gradient is n cross 1, we all know that. So, yeah, this is the gradient. Okay. So, using this we can see that h of alpha is f of x k plus alpha dk transpose del f of x k plus half alpha squared dk transpose h dk. Okay. So, just to note again, you can see that the first 3 terms are just f of x k, f of x k is what I have written here, and what is dk transpose del f of x k? It is dk transpose h x k plus dk transpose b, yeah, again these are the same. Okay. Since these are scalars, so an alpha outside. So, you have alpha dk transpose del f of x k, and then you have plus half alpha squared dk transpose h dk. Okay. So, yeah, I mean I have just rewritten h of alpha in terms of f of x and del f of x, f of x k and del f of x k, nothing new. Okay. Keep that in mind. Okay. And yeah, so this is h of alpha. Now, let us actually find which alpha minimizes h of alpha. So, h dash of alpha equal to 0 implies dk transpose del f of x k plus alpha dk transpose h dk equal to 0. So, you have alpha equals minus dk transpose del f of x k by dk transpose h dk. Okay. So, what does this tell us? It actually tells us that when you have a quadratic function in n dimensions, n could be any large value, okay, but it should be a quadratic function of the form h x transpose h x plus b transpose x plus c, where h is actually a positive definite matrix. Okay. So, if that happens, we actually have a closed form solution for the step size that you need to choose. You can give me f, you can give me x k and d k. Okay. I will give you what the step size is going to be. The step size is just minus d k transpose del f of x k by d k transpose h d k. Okay. So, yeah, that is a closed form solution, and this is something that we will use throughout the course. Okay. So, whenever we have a quadratic function, we will close our eyes and use exact line search. We will not go for backtracking line search. Okay. And in exact line search, we will use this wonderful formula alpha equals minus d k transpose del f of x k by d k transpose h d k. Okay. All right. So, this was something that I wanted to cover before going to the next topic. Okay. And yeah, so one more thing that I wanted to do was I want to define del f of x k by a notation called g k. Okay. So, this is I mean just for brevity, I mean this is used in many of the optimization algorithm literature. So, I am just going to use that from now on. So, I mean I could have introduced this before, but fine, I mean we will start with this now. So, I mean if we use this notation, alpha actually becomes minus g k transpose d k by d k transpose h d k. Okay. So, yeah, you can, I mean, I have just substituted del f of x k as gk, nothing new. Okay. So, fine, yeah. So, this is all I had to say about exact line search and backtracking line search algorithms. Okay. So, let us now get back to the original algorithm, the general form of the algorithm that we had, I mean, maybe 2-3 classes back. So, this is where it is. So, let us see where we are, that is basically what we are trying to do. So, if we are able to initialize x0 and the tolerance, okay, and somehow choose a descent direction, okay, what we have understood at this point is that this step of choosing alpha k using line search algorithms is something that we are comfortable now using exact line search algorithm and backtracking line search algorithm. The one that we are not fine as yet is in this step where we want to choose the descent direction. Okay. So, we will start learning about that from now on. Okay. Choosing descent directions. So, what is the problem in choosing descent direction? So, let us recall the example that we had again a few classes before. Okay. Yeah. So, note that when you have this particular f where you had f of f is actually x1 squared plus x2 squared and x naught is 5 comma 4. Okay. You had an infinitude of directions. So, any direction that satisfies 10 d1 plus 8 d2 less than 0 is a descent direction, right. So, that is not just a problem for this particular setting that we have considered, for this particular example that we have considered. Okay. Take any other example for that matter. Okay. So, take any f, okay, and let us say you have xk. So, given a function f and xk. Okay. So, how would the descent direction be? So, the descent direction satisfies this particular condition, right, del f of xk transpose dk is less than 0, right. So, that means, so this is let us say, yeah, so we saw that this can be written as gk, right. So, I can expand this as the set of all dk's such that gk1 dk1 plus gk2 dk2 plus dot 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 plus gkn dkn less than 0. Okay. This again is a half plane, right. So, yeah, a half plane is just, I mean, you have, so in 2 dimensions it is just a line and the area below it. So, in 3 dimensions it is a plane and the area below the volume below it and so on. So, in n dimensions again imagine that it is a plane in n dimension and the area below it. Okay. So, yeah, that is how the descent direction, I mean the set of descent directions that you can choose is going to be, that is, so it is always an infinitude of directions, is not it. So, that is bad, I mean that is not how we want an algorithm to look like. I want a specific value of a direction, right. So, how do we choose such a direction? Okay. That actually depends upon the algorithm that I am going to use. Okay. So, initially we will look at 2 algorithms. Okay. One is called as the steepest descent or the gradient descent algorithm, okay, and the other is the conjugate gradient algorithm. Okay. So, and after that we will go to further more sophisticated algorithms. Okay. So, we will start first with the gradient descent or the steepest descent algorithm. Okay. Gradient descent or steepest descent. So, yeah, this algorithm has 2 names, either you can call it gradient descent or the steepest descent. Okay. So, fine. Yeah, so we saw that there are infinite possibilities, good. The question that we should ask is which direction is the best? I mean, is there a characterization on how to choose the best direction, right? So, that is something that we can ask for. So, I claim that, okay, this particular direction, take dk equals minus del f of xk, okay, or yeah. So, by our new notation we will call it minus gk, okay. So, so now you should have two questions. One is this a descent direction or not? If it is a descent direction, by what metric can I say that it is the best, right? So, we will answer both the questions now, okay. So, yeah, let us see if it is a descent direction. So, yeah, dk transpose gk is minus gk transpose gk, right. So, that is just minus gk1 squared plus minus of gk1 squared plus gk2 squared plus dot dot gkn squared. That is always positive, that is always negative, right, unless gk is 0. If gk is 0, then we have actually attained the minimum, right. So, gk is not 0, because if gk is 0, then you would have already stopped the algorithm, right. So, for any non-zero gk, you can see that minus gk transpose gk is minus norm gk squared, which is certainly less than 0. So, minus gk is always a descent direction. All right. So, now why is it the best? Is there any reason to believe that it is the best? Okay. So, to prove that it is a good one, okay, I will use something called as the Cauchy-Schwarz inequality. Okay, I do not know how many of you have heard about this. Okay. I am not going to prove this, I mean that is not the purpose of this course, okay. You can find it in any, I mean yeah, so you can even find it in Wikipedia, okay. So, what is the result? It is just this, okay. So, when you take a dot product of two vectors, it could be any size, okay. When you take a dot product of two vectors, that is always less than or equal to the product of the norms of the two vectors, okay. So, I mean some of you might have read this in vector algebra for two dimensional vectors, right. So, dot product of a comma b is equal to norm a into norm b into cosine of the angle between them, right. So, that is true in two dimensions, and since cosine is always less than or equal to 1, you can you would say that the dot product of a comma b is the product of norm a is less than or equal to the product of norm a and norm b, right. So, it turns out that it is true for any two vectors a and b, okay, for of any size. They could both be 10 dimensional vectors, 189 dimensional vectors, whatever, okay. So, that is Cauchy-Schwarz inequality. And there is one more thing, the equality holds if and only if a is equal to lambda b, okay. So, yeah, this is not the full result. So, with equality if and only if a transpose b, sorry, a is actually equal to lambda b, okay. That is say a equal to 2b, a equal to 1.95 b, a equal to minus 3b, whatever, okay. So, if they are if they cannot be written of this form, okay, so then equality is not true, it is a transpose b is strictly less than norm a into norm b, Okay. So, that is what is Cauchy-Schwarz inequality. Okay. So, let us now ask how can we maximize the effect of decay, right. So, I mean, when do I call the decay to be the best, right. So, when you bring about the fastest reduction, right. So, that is when you call the value of decay to be the best, right. So, you can see that if you apply Cauchy-Schwarz inequality, dk transpose gk is less than or equal to norm dk into norm gk, okay. And when is it equal? It is equal only when with equality if and only if dk is equal to lambda gk, okay. So, if I restrict dk to be of a particular dimension, okay. So, let us say norm dk is equal to 1 or something of that sort, okay. Then the best way that I have is to choose it as a multiple of gk, and here I am actually choosing it as minus gk. So, that it is actually a descent direction, okay. So, at least, so what this actually means is that if you are actually choosing a descent direction, choose the direction in such a way that the descent is the steepest, okay. The descent is the fastest, right, and that is why the name to this algorithm is called as the steepest descent algorithm, right. And also the name gradient descent actually comes because so the name gradient descent because the direction is exactly the negative of the gradient, okay. So, you are descending along the gradient of f at xk, that is why the name gradient descent. So, descending along the gradient turns out to be the steepest possible descent that can occur, okay. That we have just shown because of Cauchy-Schwarz inequality, okay. So, that is why it is actually called the steepest descent algorithm, okay. So, the algorithm is as follows. So, I mean I will just write down the formal algorithm. So, of course, initialize x naught tolerance and k equal to 0, and until norm gk is greater than the tolerance. So, what you do is choose dk equal to minus gk, choose alpha k by any line search algorithm, exact or backtracking line search algorithm, okay. I will just write it as algo for the case of for the sake of brevity, and xk plus 1 is xk plus alpha k dk. I can also write it as xk minus alpha k gk, okay, and k equal to k plus 1, and output x star equal to xk, okay. So, this is the full algorithm. So, you can implement this straight away in any of the programming languages, and we will implement it in Python, okay. So, where you actually just choose I mean start with some initial value, and the direction is the steepest descent or the gradient, the negative of the gradient actually, and the step size is given by any line search algorithm, and xk plus 1 is just xk plus alpha k dk. So, you do this until norm gk reaches below the tolerance value. Alright. So, gradient descent algorithm in the next lecture. Thank you.